What if empty space isn't empty at all? What if it's actually an elastic physical medium? And that medium itself is what gives rise to the very laws of our universe. Well, today we're digging into a theory that completely reimagines the fabric of reality. You know, our universe seems to run on a very specific set of rules, these fundamental constants that are tuned with just mind-boggling precision. The weird part is, modern physics can't really tell us why they have the values they do. It's one of the biggest mysteries out there. And that really is the puzzle, isn't it? Why is the speed of light what it is and not something else? Why is gravity so incredibly weak compared to the other forces? Right now, these numbers are just treated as inputs into our equations. They just are. And if you're searching for a deeper understanding, just because is a really unsatisfying answer. And look, you don't have to take my word for it. The legendary Richard Feynman himself was completely stumped by one of these numbers, the fine structure constant. He famously called its origin one of the greatest damned mysteries of physics. So yeah, this problem goes deep. Okay, so this is where a fascinating idea called dynamic vacuum field theory, or DVFT for short, comes into the picture. It proposes this radical shift in how we look at things. Instead of seeing the vacuum of space as just a passive, empty backdrop, DVFT says no, the vacuum is the main character in this whole cosmic story. The standard view really does treat the vacuum like an empty stage. It's just nothing. But DVFT completely flips that on its head. It says the vacuum is a something, a physical medium with its own real, tangible properties. So, what are those properties? Well, the first key property is something called phase stiffness. The best way to think about this is like the surface tension on a pond. It's the vacuum's own elastic resistance to being stretched or changed across space. It really, really wants to stay smooth and uniform. The second property is called inertial stiffness. Now, if the first one was about resistance in space, this one is about resistance to changes over time. Think of it like trying to push something heavy. It's the vacuum's own inertia, how hard it is to get things moving or to change their motion. So you've got these two kinds of stiffness, one across space and one through time. Now, here's where it gets really wild. Once you say that the vacuum has these two properties of stiffness, something pretty amazing happens. You don't have to just assume Einstein's theory of relativity is true anymore. It just emerges. It falls right out of the physics of this vacuum medium. So in DVFT, the speed of light isn't some magical unexplained number that's just plucked out of thin air. It's simply the speed that a wave travels through this vacuum medium. And that speed is determined by the ratio of its phase stiffness to its inertial stiffness. Suddenly, c becomes a material property, just like the speed of sound is a property of the air it's traveling through. The logic here is just so clean. Let's walk through it. 1. The vacuum has these two forms of stiffness. 2. The ratio between them is always constant, which sets a universal speed limit, c. And 3. Once you have a universal speed limit baked into the fabric of space, the mathematics of relativity, what we call Lorentz invariance, becomes absolutely unavoidable. It has to be true. Okay, but wait a minute. If you're thinking ahead, you might be asking, hang on, if space is a physical medium, like an ocean, shouldn't you be able to measure your absolute motion through it? That would create a preferred frame of reference, and it would completely violate the principle of relativity. And you know what? That is the classic objection, and it's a fantastic question. The answer, according to the theory, lies in how this vacuum behaves. Moving at a constant speed is just a smooth, uniform drift in the vacuum's phase, and because it's perfectly uniform, it costs zero energy to maintain. The vacuum only pushes back when you try to change your motion, when you accelerate. So what this means is that no local experiment you could ever perform could tell you your absolute speed. The principle of relativity is completely preserved. All right, so deriving relativity from scratch is a huge win. But this theory goes even further. It suggests that two other phenomena that seem totally separate, inertia and electromagnetism, are actually just two different faces of the vacuum's own rigidity. Here's the core idea. What we call inertia, the thing that gives objects mass, is just the vacuum's resistance to moving a particle straight through it. But the fine structure constant, which basically sets the strength of electricity, is the vacuum's resistance to twisting its phase around a particle. It's that simple. One is about moving, the other is about twisting. This means they're not two separate things at all. Both inertia and electromagnetism are probing the exact same underlying rigidity of the vacuum, just in different ways. They're two sides of the same coin, both born from the vacuum's own internal dynamics. And you can probably see where this is going. This same logic can be extended even further. What if many, or even all, of the fundamental constants of nature are nothing more than fingerprints of this underlying vacuum medium?
This new perspective reframes everything. The speed of light, c, goes from being an unexplained postulate to just the emergent signal speed of the vacuum. Planck's constant, h, becomes the smallest possible unit of the vacuum's coherence. The fine structure constant, alpha, is no longer some mystery number but a direct ratio of the vacuum's rigidity. Even the gravitational constant g could simply be the result of the vacuum's long-range response. They all stop being arbitrary inputs and start being physical descriptions.
So, what's the big takeaway here? It means that a theory like DVFT offers a really profound shift in our whole perspective. It changes the very nature of the questions we're asking about our universe. This quote from the source material really sums it up perfectly. The mysterious numbers that govern our universe stop being arbitrary rules and instead become logical consequences of the physical medium we all live and move through. And that leaves us with this final thought. We can stop asking, why did nature pick these specific numbers? And we can start asking a much more physical and maybe even a more answerable question. What properties must the vacuum itself have in order to allow for a universe like ours to exist at all? And that is a fascinating new path for physics to explore.